All right, hi guys. Thanks for coming. I remember last class or last time we met, we said at the end I said that we talk about any biology topics that you guys want to go over. I'm gonna expand that a little bit and just say any biology or chemistry topics that you want to go over at all. Anything potentially in a class that you're taking right now, or just things you're interested in. We can talk about a variety of different things. Um, And one thing I do have kind of lined up to talk about is enzymes and some of the stuff about how they work, what they are, things like that. But before that, I wanted to follow through with what I said last week. Anything chemistry or biology related that you want to talk about? Vesper structures. Yeah, Angelina, we didn't hear anything. You can use the chat though. But yeah, we can. Mitosis meiosis. All right. I'll start with Vesper structures. I think that'll be a little bit easier or quicker to go through. And then we can talk about some mitosis meiosis as we get to. All right, Vesper. So Vesper is describing bond structures for chemicals, essentially describing their 3D shapes. It's a way of predicting what a molecule will more or less maybe look like in a 3D structure. Keep in mind that these only apply to molecular compounds, not so like those that are covalently bonded to themselves, things like that. So like carbon dioxide, oxygen, acetic acid, majority of molecules, but things that are not ionic or network covalent. So like graphite, which is a large 3D completely covalently bonded structure, not things like that. Yeah. So what does Vesper stand for? Well, valence, let me think, valence electron shell VSE, wait, Vesper. I remember this at one point. It was like, it's essentially basically saying that valence electrons are going to repel each other. Oh, it's valence shell electron. Yeah, that's my bad. Valence shell electron, something for P. Shoot. Once you understand it, you understand it. It's okay. That's what it was. Valence electron pair repulsion. Vesper. Okay, valence shell electron pair repulsion. Essentially, atoms have electrons. Electrons are going to repel. You know, like charges, all that stuff. So basically saying that since the valence electrons are what are farthest away from an atom, right? An atom would be like some positive charge in the center and then negative charge outside, right? So that negative charge outside between atoms is going to cause repulsion, and that's why some atoms, of course, are attracted to each other or repel from each other depending on the scenario. But in a covalently bonded molecule, that repulsive force is going to be the primary determining factor. Those electrons are farthest out, and that's what are interacting in Vesper. So Vesper says that when atoms are bonded together, they're going to take a certain shape that is going to maximize the distance away from each other that a molecule has. So what does that mean? Well, let's say we take a diatomic molecule, so like O2, for example, oxygen, dioxygen. That's just going to be two atoms kind of like that. And of course, they're going to have some number of bonds between whatnot, whatnot. That doesn't really tell us much because just two atoms, not much to it. Now, let's take CO2. So three atoms, triatomic. What Vesper is going to tell you is that the atoms around, the atoms will be arranged in such a way that they experience the least repulsion. So let's say, just as like an example, of course this is going to be wrong. Let's say the oxygens were like this around the carbon. So this is O, and this is CO2. The oxygens could be farther away. right? They could be, if I get this, they could be like this. They could be on opposite sides of the carbon, and they'll experience less repulsion as a result. So Vesper says that's what's going to happen. Now you might be wondering, well, we know water is bent, right? We know water has the two hydrogens at an angle to each other. I'm just going to use black again. I'll just make small black circles for hydrogen. So we know water is kind of like this, right? So why is that? Well, with that, we're accounting for lone electrons on the oxygen. So the oxygen uses some electrons in the bond between hydrogen and oxygen, but it also has other electrons, and those are still existing around the oxygen. Those are going to contribute their own bit to electron repulsion and all that. So some diagrams of water will have little electron pairs, kind of like that. And those are also going to be surrounding the oxygen atom. So that's why water is bent. And so valence shell electron pair repulsion gets complicated very quickly depending on what kind of structure you're working with. Okay, so we're going to just start with simple examples then. Let us take methane, CH4. First of all, how many atoms do we have? We'll start with the really basic, and then we'll work our way to the structure. How many atoms in CH4? 5, yeah. So with 5 atoms, what can you do with 5 atoms? Like, you might think perhaps the least repelling structure would be like 5 atoms all in a row or something like that. Usually, you're going to see that the central atom is generally not like, I guess I'll call it a peripheral element. Essentially, elements on the far left side or far right side are generally not central elements. So typically carbon always behaves as a central element. It'll be in the center of a certain structure. Typically, nitrogen could sometimes act as a central thing. Yeah. So Amos, as you bring up, C is in the middle, H surrounds C. H is always a peripheral structure. It's never in the center, unless it's like H2, in which case there's not much to it. Hydrogen, I'll just make the small black circles again. So then basically these small hydrogens are going to surround the structure, right? In some arrangement. Now, what arrangement would make these hydrogens most spaced out? And keep in mind this is a 3D structure, so you can try imagining the hydrogens around the carbon in a 3D manner. What would cause the hydrogens to be most spread out? "90 degrees. So Amos, what you're suggesting, is it like you have a carbon in the center and then you have 2, 3, 4. It's kind of like a cross. Approximately 90 degrees. Yeah, so with that is pretty spaced out, except that you're thinking about it spaced out on like a 2D plane, right? All the atoms here are lying on one plane. But remember, you have 3D space, so that means you can actually get farther. So what actually goes on is a 3D structure, which is called tetrahedral. Kind of like you got 3 atoms that go like this, then one like that. I'll do my best to draw it out. It's gonna be a little rough, but hold on. All right, so it's gonna be like kind of like this. This. Now, both of these, I'm gonna say these bonds, I'm gonna say are in the plane. Let me draw on the atoms here. So you have carbon in the center, hydrogen, hydrogen, and then there's one one hydrogen that's going to be kind of pointing out. So how I'm going to represent that, it's like a little triangle. It's not the most perfect representation, but this is a common usage. The triangle is meant to say that this atom's pointing out of the screen a little bit. And I'll draw on that hydrogen too. And then there's going to be one atom that's kind of pointing like into the screen. I'll use a dotted triangle-ish shape to represent them. I'm using these weird shapes because that's going to be chemical standards. Like when you see diagrams of molecules, this is the kind of structure that you'll be seeing, triangles and little dotted things. Oh, there we are. So yeah, I'm going to shade in this triangle. At least try to. Yeah, like that. So triangle means that it's pointing out of the screen a little bit. Angelina, to answer your question, triangle is pointing out of the screen a little bit. Dotted like lines going like that means pointing into the screen a little bit. The exact magnitude is unsure. Not by the diagram could you ever really tell. But basically you can kind of imagine this like where you have one atom just pointing directly outwards. And then there's this one that's in line with the one directed pointing upwards. And then there's one sticking out a little bit, and then one sticking behind a little bit. So then you have like this pyramid kind of structure. Well, let me see what I can find on tetrahedral chemical structure. Oh yeah, this is a good image here. I'll share my screen. It does represent 3D. It's trying to represent 3D structure on a 2D plane. Yeah, this is what I'm trying to draw out. This is an example of those triangles and hashed triangles. It's meant to represent this atom is sticking out of the screen a little bit. That atom is sticking into the screen a little bit. And this is a 3D structure involved with it. A bit of like a little pyramid thing. And this is what's called the tetrahedral. The tetrahedron. Right, if I search a tetrahedron right there. So that's what we see right here, just in a molecular structure. And this is what allows these hydrogens to be most spaced out. So yes, the cross would be most spaced out on a flat surface, but with a tetrahedron, you have them spaced out 3D in a 3D structure. And notice that each of these angles is going to be the same. Each of these angles is, as this diagram says here, it's 109 degrees, 109.5 degrees. So if you think between each hydrogen and HCH angle, each one of those is going to be 109 degrees. All right, so that's 4 atoms. So CH4, so that's 5 atoms in total. Let me think. I'll get rid of these ugly things now. Usually with 3 atoms, actually no, we just went over there, right? Usually with 4 atoms. So like, let's say the one compound I can think of with 4 atoms is BF3, and BF3 is kind of weird. And that's the only reason why it exists. But BF3 and other structures with 4 atoms in total, they're gonna have one central atom and then 3 atoms around that one center atom. So how do you guys think a molecule like that would be most spaced out? If you have one central atom and then 3 around it, how would you space those 3 atoms around so that they're most far away? Triangle, yeah. So you will have like something in the middle right there. And then you have 1, 2, 3. And then these angles, so like, let me draw the angles out. So like, you have this, and then like this. That angle is going to be 120 degrees. So kind of like a triangle. 120 degrees here, and then 120 degrees like that, 120 degrees like that. So overall, 360, as you'd expect. And that's most spaced out because if you imagine, let's say you have, oh, it's really hard to do little hand things. Okay, let's say you have it like this. So one bond, second bond, third bond, and you move this in a little bit. Right away, all the atoms are closer together. So essentially, you cannot space it out anymore. This is flat, like unlike the last one. The last one was in 3D space. This one happens to be flat, but that's because the flat structure is most spaced out. Like if you try moving it in 3D space, so say like this, if you had three atoms, kind of like a little small pyramid, that's not spaced out because they could go like this. They can flatten out. And then once you go beyond that flatten out point, then you start having repulsion happen again. So therefore, the flat structure is most spaced out. All right. Now let's start getting to some weird ones. Let's say I have pH5. I'm not sure if that exists, but we'll say for our purposes it does exist. Essentially, a central atom, phosphorus, and then 5 hydrogens surrounding. How would you arrange these 5 hydrogens? Pentagon. Okay, pentagon, once again, it falls into the same thing with the square, like the cross. It's not very spaced out because it's in like a flat thing. Pyramid. So how would you shape it? Like describe what kind of pyramid you think of. A square. Oh, so do you mean like, oh, like a square pyramid? So like this kind of? So like each of these atoms? Yeah. So let's think about that. I'm good. This is our central atom again. I'll put down little atoms. You can tell kind of right. Oh, that one's not very good. I'll put it in like. So this is the central atom, and then we have bonds going backwards. For this one right here, it's going backwards. For this one right here, it's going backwards. Here it's going forward and going forward. So it's like a square pyramid. The thing is, let's say I take that. Oh yeah, that's only 4. My bad. Yeah, that's only that. Yeah, Angelina brought up a good point. That's only 4 atoms, not 5 atoms, around the central atom. Also, yeah, it doesn't make sense because it's very close together. Like you could space it out pretty easily. Okay, yeah. 5 is kind of hard. It's hard to visualize. Like usually people learning this for the first time, it's almost impossible to think of. It's just a weird structure, and I'll show you guys what it looks like, and you guys will be like, "Oh, that's why it's most spaced out." It does make sense once you realize. Oh, Amos searched it up already. All right, yeah, 2 pyramids, kind of like this. It's like 2 pyramids on top of each other, a little bit. So like that, like that, like that, like this. This is a GIF, so we'll be moving around. You notice how when it restructures, so when it's in this position, it's the same as that position. Just imagine it. It just means that the straight line is this way instead of this way, but it's the exact same structure. Yeah, this one's doing the same thing. I don't know what's up with that rotation that everyone's so interested in. Yeah, see, this demonstrates how it's the exact same molecule. Basically, that's the most spaced out you can get. This is the most spaced out you can get. So yeah, it's a funny looking thing. So like a triangle with 2 hydrogens protruding. Yeah, kind of like that. One thing you might notice is that the bond angles are not all even anymore. So like this is a 90-degree angle right here, but that is 120, right? Here, that shows a 90. But then the one, oh no, that's a different structure, not that. But still, 90 and 120, the angles are a little different. And that's why if you go over here, this also points out that there's 2 different kinds of atoms here. These 3 are what are called the equatorial positions because they're like, if you think about like the equator, it's like in the center, it's flat. And then there are the axial positions that are a little farther. So let's go back to that repulsion idea again. Like let's say I take this atom right here. It's being repelled by each of these atoms, each of these 4 atoms nearby. Same with this atom, same with every other atom. Would an atom on the equatorial position, would an atom right here or here or here, would that experience more or less repulsion than an atom right here? I'll repeat that. Will an atom here on the equatorial position experience more or less repulsion than an atom on the axial position? And for our purposes, we'll just assume that it's the exact same 5 atoms surrounding the central. What do you guys think? All right, Amos, you said less. Which one receives less repulsion? Are you thinking that? Equatorial receives less. All right. Angelina said axial sees less. So we got a bit of a conflict, and we'll see which ones are right. Okay, so I'm going to first consider an equatorial. We're going to consider this red one right here. All right, so this atom and that atom are the closest atoms to this one, right? They're 90 degrees away. They're very close. This atom is 120 degrees away, and the one back here is also 120 degrees away. So we have 2 atoms that are 90 degrees away, so pretty close, and then 2 that are a little farther away, 120 degrees. All right, I'm going to change color to blue. All right, now let's consider this axial atom. This atom is 90 degrees away, right? Axial, equator. So that's 90 degrees, that's 90 degrees, and that's 90 degrees. So you have 3 atoms that are 90 degrees away. And you have one that's 180 degrees away. Angelina says she changes her answer, and she is correct in changing her answer because it is the axial positions that experience more repulsion. Yes. So axial atoms do experience more repulsion than equatorial atoms. They are in a different state, technically. So this is a bit of a tangent, but it is, I think, interesting and potentially enlightening because it talks about modern technology. So there's something called nuclear magnetic resonance spectroscopy. So let me quickly. Nuclear magnetic resonance spectroscopy, these are like different graphs versions of it. Essentially, it's a way of detecting different states in a certain molecule. So for example, CO2, there's the carbon and there's an oxygen, but the 2 oxygens are in the same state, so this is the same. Whereas if you have, say the oxygens were in different states, then NMR would register. For this particular kind of molecule, let's say we take pH 5. The hydrogens will register 2 different states because there are 2 different states. There's an axial state and an equatorial state, and they are different. So NMR is like a non-invasive way of detecting certain diseases, but it fundamentally stems from detecting chemical states. And it's able to detect the difference between these 2. Anyway, it's pretty interesting. And a common question that they usually ask on the US NCO, whether you're taking that or not, I think it's interesting that they ask specifically about molecules like this, and then they ask things like which one is like which atom here is going to be furthest away from the central atom. Now, using our reasoning that axial is repelled more, the axial bonds would then be a little longer, right? More repulsion, a little bit farther away. The axial bonds on this molecule are going to be longer than the equatorial bonds. And then sometimes there's a bunch of math, geometry and stuff. That's a common US NCO question. Just a little interesting. Little tidbit about bipyramidal structures. And that's another thing. I haven't really been talking about names. I'll do that now. So let me quickly draw a 3-atom structure. I'm not going to differentiate between the atoms now. But this is our 3-atom structure, right? Keeping the most distance by keeping the atoms flat. That's a 180-degree bond, right? This is 180 degrees. So we're staying farthest away as we could possibly stay. This is what's called a linear molecule. So angle equals 180. All right, and then when we get to 3 atoms around the central, so like that. We also talked about this, kind of like boron trifluoride, so BF3 would be an example of this kind of molecule. Oops. No, so not straight. It's okay. You guys get the idea. This is what's called Trigonal Planar with an A, not an E. That's my typo. Angle being 120 degrees. Trigonal, triangle, just a variant of that. Planar meaning it's in the same plane. It's in one plane. All right. And then I am going to try to quickly draw one of the tetrahedrals. Right. This is what's called tetrahedral. Angle is 109.5 degrees. Don't need to memorize that. That just happens to be what it is. All right, now we're getting to 5 atoms, so things getting a little weirder. Our molecule, oh, that's not straight. Molecule's gotta look kind of, that'll do. Have like that, one sticking out, right? Then one going inwards. That is going to be called Trigonal Pyramidal because it's triangular, right? The base is triangular, 1, 2, 3, equatorial. And the bipyramidal just means there's 2 pyramids, right? It's like 2 pyramids on top of each other. Angle is going to be either 90 or 120, depending on what angle you're looking at. All right. Now let's talk about 6 atoms around a central thing. What will be the most spaced out version? What do you guys think? I think this one is pretty doable. Like looking at this pattern of keeping it farthest away, it might be, I think it's plausible that you guys can come up with the 6 atom arrangement. So for example, sulfur hexafluoride, that's a common chemical used for a variety of reasons. SF6, so a central atom of sulfur, and then 6 fluorine surrounding. What would be that structure? What would be most spaced out? All right, no answers. I'll just go into it then. It's going to be what we call octahedral. I'm going to try drawing it out. So that just looks like a star, but I'm going to try adding a bit of a 3D effect to it, and then you'll see what I mean. These two are going to be, come on. Drag it. All right. These are sticking out of the page, or sticking into the page, my bad. These bonds are sticking into the page, and then this is sticking out of the page. So basically, it's got like, it's similar to the trigonal bipyramidal in having that central axis, but then the base is across. The base is kind of like a square. All right, so I'm just gonna bring up an image instead of keep on trying to draw this. Octahedral structure. Just like that. So that's 6 atoms, most spaced out. Every bond angle is 90 degrees. And yeah, that's 6 atoms. Usually, molecules don't get much more complicated than 6 atoms. This is pretty much the peak. So that covers the basics of Vesper theory. Let me think if we get atoms. Acetic acid structure. Oh, come on. 3D structure. So in this one molecule, you can see that there's a lot of the different patterns we talked about. This carbon is the center of 4 different atoms. So that is what we see as the tetrahedral structure, right? Here we have Trigonal Planar, right? And then here we have this bent thing. Now, remember we talked about 2 atoms being 180 degrees, not like this bent thing. That brings us into our next idea with the valence electrons, briefly mentioned earlier. So far, does everything make sense? Everything's coming along fine? Any questions? All right. Angelina says yes. Amos, I'm assuming you say no to no questions, so I'll keep on going. All right, anyway. If there is a question, just feel free to bring it up right away. So, going to electrons. Now, let's think about oxygen. Oxygen, if you guys look at your periodic table, you'll see that there are 6 valence electrons. So, hydrogen, we know, has only 1 electron. You can't say it's valence, really. It is valence, but not really, because it's the only electron that the atom has, so there's not really valence or core electrons, it's just there. But anyway, so we have 1 electron from hydrogen, 1 electron from this hydrogen as well. Oxygen has a total of 6 electrons. I'll draw them evenly spaced around the oxygen for now. So oxygen is of course going to form a bond with hydrogen to form water. And a bond, it consists of 2 electrons. So each atom is going to contribute its own electron, like that, like that. All right, so what happens to these 4 electrons around oxygen? Well, they kind of pair up, and the reason for that has to do with quantum chemistry, about upspin and downspin of electrons and how they're arranged. So quantum is outside my expertise, and I know only very little about it, but they pair up, bottom line. So I'm going to erase these electrons now. I'm going to draw them paired up together. So there's 2 electrons paired together, and here are 2 electrons paired together. And the idea I'm going to introduce to you guys is that paired electrons, these are what are called non-bonding electrons. An electron pair is going to act similar to a bond. Like a bond itself is only 2 electrons, right? So it makes sense for it to act similar to a bond. But basically, it's going to act like another atom in a sense. Basically, it's going to act in repulsion with the other elements around the center atom. So what actually goes on with oxygen is that you can treat this kind of like methane, right? H, C, H, H, H. This came out to be the pyramid thing we talked about, right? It came out to be tetrahedral. Oxygen is going to do a very similar thing. What actually goes on is that 2 electrons kind of behave as if they're like a ball. So kind of like that. Hydrogen, of course, taking up the other spots. So this hydrogen is pointing backwards, this electron pair is pointing forward. These two are in the plane of our drawing. So this is tetrahedral. The thing is, the electrons are, of course, not atoms. They do repel like atoms, right? There are two electrons. They're negatively charged. They're going to be repelling with other negatively charged things. But they don't really they're not atoms, right? So when we actually look at the atoms involved in this structure, remember how all the bond angles in this structure are 109.5 degrees? This bond angle for the hydrogen, just imagine it going behind the oxygen, that's 109.5 degrees. If we just look at the atoms, so I'm erasing the electrons, it looks as if the molecule is bent. So you have your oxygen, you have your hydrogen. That angle is 109.5 degrees. And that's not out of nowhere. It's not like it's breaking Vesper theory. Vesper's theory is still being upheld. It's because there are electrons. Oh, that's not an electron. There are electrons coming off of this molecule that are also repelling the hydrogens away. Kind of like that. Make sense? Electrons are just going to pair together, and then once they pair together, they're going to repel similar to an atom. So this structure is what's called bent. It's pretty intuitive. It looks like a bent molecule. Another structure that exhibits this kind of thing is Nh3 Ammonia. So that's not it. I'm going to draw a quick Nh3 diagram. Central nitrogen. Then we have hydrogen, Nh3, so we have 3 hydrogens. But the thing with nitrogen, right, nitrogen has 5 electrons, and it's bonding with 3 different hydrogens, right? So hydrogen each has 1 electron, but then times 3, so that makes 3 electrons. So nitrogen is going to use 3 of its own electrons to form bonds. So if I draw that in real quick, you have electron here, this one from the hydrogen, this one from the nitrogen. Same thing over here, same thing over here. Nitrogen has 2 electrons remaining, and those 2 electrons are going to pair up, and they're going to do their own thing. So what we actually have is once again a tetrahedral structure, but the tetrahedral structure arises from electron pairs. If you look at the atomic structure, you will not get tetrahedral, right? There's only 3 atoms. So here you have your tetrahedral structure, but only looking at electron pairs. Once I erase this, you'll notice that the 3 atoms kind of bend inward. And then there are the electrons right here, right? Electrons repelling these so that they're not flat. They're not flat like you'd expect with 3 atoms around a central atom. They're bent inward, very slightly. So this is what is called Trigonal Pyramidal. And that makes sense, right? Triangle, 3 atoms, trigonal, but it's also a pyramid. It's kind of like this. So does that look like a tetrahedron missing a diagonal? Yeah, pretty much. Let me pull up a quick image. Search up Nh3 3D structure. There we are. 107 degrees. Okay, that brings me to another point that I'll mention really quick. So notice that without the electron. Here's another representation of the electrons. 106.8 in this diagram. So without that, I'm gonna go quickly search up CH4. We know that it's 109.5. But with this, we see that's a little less. And that's because electrons, so just an electron pair, is going to repel more than an atom. Right? Two electrons are going to repel more than an atom. And that's because an atom has some positive charge and some negative charge, with the negative charge being farther out, so therefore a little more influential. But electrons are just electrons. They're literally localized negative charge. So they're going to repel a little more. And Angelina, you once again asked why. Like, it's hard to visualize why it repels more. It just does. And the reason is experimental data. Scientists noticed, yeah, it's fine. But it is an important point. Scientists did not say it makes sense that electrons repel more. It just so happens that that's what real life looks like. They measured molecules, used different strategies, and found these bond angles. And they're like, the only way we can explain it is that electrons repel more. And that's a principle that carries throughout any structure. Electrons will cause the structure to have smaller bond angles other places in general. All right. Let me think of a good molecule that we can use for visualizing some things. How about like BRF5 reduction? That is not it. No, that's not correct. So this kind of changes my plans a bit. What I was going to do is show you this structure and then say, look at how the electrons are not in this structure. But then turns out it's this structure. Wait, let me think. I want to find something that does represent what I was going to predict, because it is important. ICL5. Okay, I guess this kind of brings me to a different point. But anyway, let me first share what I was planning to say. What I was planning to say was that when you have an electron pair for the 5-atom thing, right? Let's say you have 4 atoms and then 1 electron pair. So here's your typical bipyramidal structure. Hopefully you guys don't need the 3D notion to be able to see what's going on here. This is a triangle. These 3 are a triangle, then this is sticking out. So you have equatorial, and then, axial, equatorial. And then one of these is going to be an electron pair. And I was going to say, do you think it's axial or equatorial? And then it's going to be equatorial because there's less repulsion, right? Electrons repel more. So it would make sense for them to want to be farther away from the atoms. And then the equatorial, remember we talked about equatorial atoms are farther away or less repelled than axial atoms because they're farther away from the bond angle. And then I searched up that diagram, and then you guys saw that it's not the case, and that it will form a square pyramid. Wait, that's not it. Hold on. ICL4. It's not I. Yeah, see, this brings me to that point where the structures are not set in stone. The rules don't always work. Oh, here it does though. Okay, so SF4 is kind of weird. It's what's called a seesaw. You can imagine the last atom sticking out like that. And then you'd have your trigonal bipyramidal. This is where the electrons are taking up space. So that's where the electrons are. In order to prevent repulsion, you know, if it was over here, then there'd be atom here, here, here. It experienced a lot more repulsion, so therefore it sticks with equatorial. The thing is, if I go back a bit, go to this. Let's go to this one. This one's also kind of explainable because electrons repel more, right? So if you imagine this is the octahedral structure, 6 things around the central atom. If electrons were over here, then you'd have electrons closer, which means more repulsion. Whereas if you have them on opposite sides, then you have less repulsion. And of course, they're being repelled by the chlorines. Yes, that's true. But they themselves are farther away from each other. So that creates overall the least amount of repulsion you can find. And then if we go back to ICL5, yeah, this also makes sense now because the electrons are just taking the spot of one of these chlorines, or like one of the 6 positions around the central atom. All right, we hit on a bunch there. Any other questions that you guys have? Like specific questions on things that don't really make sense yet? Because that was quick, I understand. So, anything you guys might have questions? All right, are you guys good? Oh, so just to recap, Vesper structures just detail the layout of a molecule. Yeah, that's pretty much all they do. There's another thing called Lewis structures, which is basically a way of representing Vesper structures, but it's like a related topic. Yeah, Lewis dot structures or Lewis bond line structures, things like that. It's another way of representing molecules. Any questions about like how Vesper really works? So fundamentally, you can just remember that Vesper is all about repulsion, keeping everything as far away from each other as possible. You can't really go wrong with that, as long as everything's farthest away it could possibly be. It's good. All right. We don't have much time for mitosis or meiosis anymore. I'm sorry. Yeah. For mitosis and meiosis, it comes into the area of things that a video online can probably explain better than I can. So once again, I'm gonna bring up Amoeba Sisters, which I brought up a few times. Amoeba Sisters covers mitosis and meiosis very well, very, very well. If I were to explain it right now, I pretty much just repeat their video. So, Angelina, have you checked that out already? The Amoeba Sisters video on mitosis and meiosis? Because I think that would be your... Okay, if the last time you watched it was in 7th grade, then potentially you might want to rewatch the mitosis and meiosis video, because they have like an updated one that's really detailed and good. Explains everything very well. All right, so let me think. Anything else that you guys want to go over? Because the other thing I want to bring up about enzymes, yeah, we're not gonna have time for that either. So, any other quick topics? Or nothing? Well, if there's nothing, then nothing we can do is see how quick I can explain enzymes. So this kind of describes enzymes in a graph form. But this doesn't make much sense if we don't know what enzymes are. So enzymes, bottom line is, this applies to both chemistry and biology because chemistry also has things called catalysts. And some of these principles work for catalysts as well. Enzymes are essentially just biological catalysts. They speed up reactions. And the way they do that is by increasing the rate of both way reactions. So catalysts can work in a variety of ways, and enzymes are a specific kind of catalyst that work in specific ways. For example, a platinum catalyst, what it often does, it takes hydrogen, and then you know how hydrogen is bonded like this, right? Like two atoms bonded together. The hydrogen comes close to the platinum surface, and then this bond between them breaks, and then they form bond with platinum. So then that creates a lone hydrogen, which then another atom, say like some kind of carbon-based atom, will then react with and then get a hydrogen like that. So it speeds up that particular reaction by providing a different pathway through which two atoms can react. So like hydrogen by itself, like H2, wouldn't react with a carbon-based molecule by itself. Like you wouldn't break that hydrogen bond and then form that other bond. It just doesn't make sense. Whereas that catalyst way takes a little bit less energy. It's a little more favorable. So that's what catalysts do. They speed up reactions by making a different path through which the reaction can occur that is more favorable. Enzymes basically do the same thing. They're like complexes, big complexes of molecules where they attach to some molecules and attach to some other molecules, and then they change shape so that these two molecules can react. And that sounds very vague because it is. Every enzyme is very, very different. And a lot of university professors, what they do is choose like a certain family of enzymes and literally just study those enzymes to figure out exactly how they're working. And they make a living off that because enzymes are just complicated. It's still a field of study that are very that's still growing. From what I've seen in Campbell, biology is very vague. Yes, I'm not going to deny that. It is true. All right, so where do Lineweaver-Burke plots come in? This is for enzyme inhibition. Essentially, there are certain molecules that can deactivate enzymes in some way or another. And there are different ways through which they can do it. So a common drawing for an enzyme, I'm just going to do like this little thing. It looks like Pac-Man. That's going to be a common illustration of enzymes. It's not actually what enzymes look like, right? If I were to quickly search up a picture of an enzyme molecule, enzyme molecular structure, you're going to see the rainbow in molecule form. This is an enzyme. It's hard to tell exactly what's going on because a lot of stuff is going on in every enzyme. Basically, this certain complex of molecules will receive another molecule called a substrate, and then the enzyme is going to change shape. Then substrates will then be positioned to somehow react in some certain way. Enzymes are very big, as you can tell. But bottom line, they speed up reactions. So Lineweaver-Burke plots describe the behavior of enzymes quantitatively. So what's kind of going on here is, so let's just ignore the changing slopes for now and just look at the units, or the, sorry, not units, the axes going on here. There's this and there's that. So this boxed S, if we remember from some of the other chemistry stuff we've done, the box means concentration. So this is basically saying the concentration of substrate, the S, that we have going on. Substrate just being the receiving molecule. Enzymes go receive a molecule, right? And it's going to do something with it. That molecule that's being received is the substrate. So how much of that substrate do you have, bottom line? That's what the box S means. 1 over this value. That's going to be our horizontal axis. The vertical axis is going to be 1 over V. V is going to mean the velocity of an enzyme. So basically, how fast is this enzyme processing the substrate? It's not like an actual velocity, like you're not driving a car and it's like 50 miles an hour or something, like a very direct speed. This speed is like, how fast does this machine work? It's a little not hard to imagine. It's not like physical speed, but it's a speed nonetheless that you can measure with an enzyme. So the funny thing with these graphs is that it's 1 over S, 1 over V. So you're not comparing substrate with velocity. You're not comparing them directly, because what you actually get out of that kind of graph is like this, and it's like hard to read. So scientists typically express the relationships of enzymes through 1 over V and 1 over S. It makes for a straight line, and so it's a little harder to read, but it's more useful. So if you have a high concentration of substrate, so let's say this S value is very large. What does that mean for 1 over S? Will 1 over S be very large or very small if S is very big? It's going to be very small, yeah, that's right, Angelina. Because 1 over X, for example, if X is big, like X is 100, 1 over 100 would then be small. Whereas if X is small, so like X equals 0.5, 1 over 0.5 is 2, so therefore it's bigger. So everything's inverted on each of these axes. So this point down here just means high velocity, high concentration. This point up here is low velocity, high concentration. It's a little hard to get used to, but it's more convenient in the end. So what this graph really tells us is a relationship between the substrate concentration, how much substrate we have, and how fast an enzyme is able to process that substrate. All right, and now we have these different kinds of inhibition. Something going on. Don't know how much of these I'm going to be able to get through, but we'll see. Competitive inhibition, the best way I can describe it is what the name says, competitive. So let's say I have my enzyme, I'm draw a little thingy again. Then I have the molecule it's meant to receive. So it's meant to receive this blue molecule and process it in some way. And that will determine the velocity, etc., etc. Now let's say you have this competitor, this inhibitor. It's a red molecule. And it's very like the blue molecule, except that when it gets bonded to the enzyme, it gets processed, but doesn't produce the product you want. So essentially, it's like a mulligan. It doesn't actually work. It's like a false product. So this molecule is also gonna bind with the enzyme. So it's gonna compete with blue molecules to bind to this enzyme, except that's not actually gonna produce the product you want. So that means that at a certain concentration of blue molecules, as long as you still have red molecules there, you won't be processing at the same fast speed. So that's why we can see with the inhibitor graph, the slope increases. Then you might be like, why does the slope increase if we're going slower? Well, remember, this is 1 over V. So slope increasing means smaller velocity at every single point. We notice that the Y-intercept is the same. So what does the Y-intercept mean? Well, Y-intercept is what's called a V max. The way to think about it is, what does 0 mean on 1 over S? Right? If we think about, I'm going to once again go back to variables. 1 over X. When is 1 over X 0? When is this equation 0? Never. Yeah, it's never a 0. But it only can get very close to 0 when X gets very large. So let's say X is 3 million. That's very close to 0. If X gets bigger, 10 million, it gets very closer to 0. So basically, when S is infinite concentration, then we reach our Y-intercept. Essentially, this Y-intercept is the maximum velocity that can never be reached by the enzyme, because an infinite concentration is just unfeasible. So that means that there's a certain cap to the velocity that we experience. So 1 over V max, I'll call it. Remember, it's 1 over, right? So whatever this V max is. Essentially, what this is saying is, when you have a high enough concentration of blue molecules compared to red. So let's say you have a million blue molecules in a very confined space, but you only have like 2 red molecules. The 2 red molecules are not going to make a big difference to the rate at which the enzyme processes blue molecules, right? In the end, if your concentration is large enough of blue molecule, the inhibitor doesn't really inhibit. So you're always still able to reach or approximate that same maximum velocity. So the maximum velocity, this y-intercept, is going to stay the same on this graph. But beyond that y-intercept, when you have a greater number of red molecules in comparison to blue molecules, like up here, for example, you'll see a noticeable difference in the velocity. So between these 2 velocities, same concentration, but this velocity is higher because 1 over v is smaller. 1 over v is smaller, so that means that velocity is still higher. So after the inhibitor happens, each velocity is going to be shifted upward. At the very high concentration of substrate, though, it'll have less of an effect. I'm going to jump to non-competitive inhibition real quick. Non-competitive inhibition is where the molecule, like this red molecule, instead of binding here, what it does is it attacks the enzyme itself. It bonds to the enzyme. And what that causes is that the enzyme is now going to change shape. So let's just say it changes to this shape now upon binding. You might be like, how does it change shape? Well, that's with like molecular reactions that enzymes can change shape by like bending their molecular structures and stuff. Once again, enzymes are very complicated and stuff. So this thing might change shape. And once it changes shape, the blue molecule cannot bind to the green molecule. So that is what's called non-competitive inhibition. Angelina, to answer your question, uncompetitive inhibition is where this substrate, I think what it does is like, what was it? It binds to the enzyme, but it only does so when the enzyme has received a blue molecule or like the recipient molecule. It's a very like more niche kind of inhibition. Doesn't come up very often, especially not on USA, but it barely, I've never seen it come up in practice tests. And in the real world, I've never seen it come up. Competitive and non-competitive have come up though. Yeah, Campbell's limited. But anyway, non-competitive. Campbell is not, when I say it's limited, it's like it covers a lot of stuff, pretty much everything you need, but it can't cover everything. It covers like 90% of what you need. Anyway, non-competitive, it binds to the enzyme itself and causes it to deform. So the behavior of how it changes this graph will then be also different. Now, since these molecules can bind to the enzyme, you have less enzymes working. So therefore, even at the highest concentration possible, you will be working below the non-inhibited state. So that's why we see the y-intercept now changes. The y-intercept is now higher up. And remember, this is 1 over. So higher up means smaller. So Vmax is now smaller. Your maximum velocity of enzyme is now smaller than it used to be. It can't produce, even at its top potential, it can't produce as fast. Notice that this point stays the same. This point has another significance that, since of time constraints, I won't go into, but this point stays the same. So you're kind of just pivoting a different way. Whereas this graph, you're pivoting at the y-intercept. Here, you're pivoting at the x-intercept. Uncompetitive is much more niche, so it's not as essential to go over right now. Feel free to search up some of these things yourself if you're interested, to explore competitive, non-competitive, uncompetitive, a little bit on your own, see what's going on with these. Anyway, a very quick overview of some enzyme principles, mainly the math behind enzymes, because usually with like AP Bio or something, you just learn enzymes catalyze reactions, and that's about all you really need to know. And then you learn about enzyme pathways, things like that. And you can go into cell communication. It's a little bit different. Whereas with, like, say, USABO, you go into a little bit more of the quantifiable parts of enzymes. Anyway, that a little bit over time, that's okay. basically wraps up our discussion today. That reminds me, before you guys leave, I do need to ask you guys, next week I won't be able to do Friday. There's a school event that I need to be going to. Would Monday or Tuesday night, same time, 7:30 to 8:30, would Monday or Tuesday work better? Would one of those days work for you guys? Now, if you're not planning to come, that's okay. But if you are planning to come, do let me know what day works, so we can do that day. So Tuesday, you say, Angelina? Because yeah, Wednesday, Thursday, Friday are not gonna work for me. Also, consequently, next week is going to be, I think, last day of our discussion workshop line. The original end date, I think, was meant to be 17th, but I can't do that day, right? So next week's going to be that last day. Think about some of the things you guys might want to talk about. I think it'll be similar to today. We're going to talk about things that you guys want to talk about and go over some stuff. So yeah, looks like Tuesday's the day. I know that Larry didn't come, so I'll get in contact with him somehow. Anyway, that wraps us up for today. So thank you guys for coming. Talked a bit about Vesper, talked a bit about enzymes. If you have any questions, feel free to email as always. And I'll see you guys next week, Tuesday. Bye.